All right, folks, good afternoon. I'd like to start off with a quick bit of my market research. Can I just ask you to raise your hands if you know what virtual reality is? Most of you, that's good. Now, for those of you that don't worry, there's a couple of videos in this talk which will make that a lot clearer. For those of you that do, just imagine using that technology and applying it into the nuclear industry, more specifically into the nuclear design process. Well, my name's Qasim Kapasi. My job at the UKNNL is to take this technology and nuclearize it. So it's probably worth explaining the current design process. So a customer comes to NNL with a problem. A group of NNL's finest brainiacs come together, discuss that problem, come up with some potential solutions. After that, we create a lot of 2D computer-aided design models, a lot of clever calculations, and a lot of reports. After which, we create some simple mock-ups to try that experiment in a safe and risk-free environment. Now that process keeps going round and round until every one of those brainiacs is happy that the solution meets their required conditions and poses no risk to our final end user. Now there's a few issues with this current process. Those 2D CAD models can get very complicated. Now to someone who's not familiar with the process, it can take a lot of time and by extension a lot of money just bringing them up to speed. Our clever calcs, we've got some of the best calcs in the world, but we apply pessimism to every single step. That results in inflated figures, requires a lot of over-engineering. Again, takes a lot of time and a lot of extra cost. Doesn't add much to the safety. Those simple mock-ups, very simple by nature, not really representative of the proposed solution. So, in a nutshell, it's a 20th century process. It's in need of an upgrade. NNL have recognized this, and as such, they've commissioned a number of internal research and development projects focused on bringing this design process into the 21st century. So this project is focused on developing our digital reality capabilities. It's focused on two strands, our augmented reality glove box and using Holden's virtual reality dose planner. So strand number one, our augmented reality glove box. Now that's being developed in collaboration with the Nuclear Advanced Manufacturing Research Centre down in Sheffield with the intention of training operators and testing out experimental routes in a risk-free environment. The system consists of a metal frame outlining the dimensions of the glove box, a physical barrier with apertures in the middle to provide that realistic experience with glove port locations, constraining the operator's movements. 8 infrared cameras dotted around the place, which track the motion of sensors which can be placed on the fingers or objects of interest like cylinders or even if you want a Concorde. And all that is viewed in a HTC Vive, which provides that fully immersive, fully virtual experience. So our hardware, plus our CAD models, plus the details and inventory of our experiment. Meshing all these three things together results in a fully immersive augmented reality experience, which is the video and should be working. Results in a fully immersive augmented reality experience where the user can test out that route in a risk-free environment without any of the associated risks. There we go, the video works. Now here, he's working in the actual environment, but what he's seeing is, you see in the bottom left-hand corner, that's in the virtual scenario. Now it's in its early stages of development. So one of the added features of this, it will be able to record the dose uptake whilst performing the activities in that virtual environment. So you can place a virtual source, perform experiments in that virtual scenario, and the computer will calculate the dose and the time, and that data can be fed back into our process. So that's what we have. Why do we need it? Well, currently, to get a glove box operational costs up to £1 million. This project has the potential to reduce that cost, reduce the time, increase the accuracy, increase the safety, increase the efficiency. It's a win-win scenario. Why would you not want it? So that's strand number one. Moving on to strand number two, using Holden's virtual reality dose planner. So it's a software developed by the Institute for Energy Technology at the Holden Virtual Reality Centre up in Norway. Essentially, it's a dose uptake simulation software. Now within it, the user would create the CAD models, import the CAD models into the software, set the scenario. So you can set the shielding properties. So here we've got a lead container, a lead cylindrical container, a yellow container there. We've got some walls made out of iron and concrete. Set the source properties. So we can set of various inventories, of various isotopic inventories. They can be anything from point sources to line sources to simulate a leakage, say for example. Now, what the software does, it calculates the dose that each of those operators is exposed to in real time. Now, one of the added benefits of this is providing the results to the end user. We can do it in the form of graphs, or we can do it as a video, like the ones you've seen right here. So instead of explaining to the end user how this works, we can actually show it to them. So show them that the operators will take this route, and the results can be compared to the other routes. Now, those results can be displayed in the form of graphs if you need it for reports. So you can have the accumulated dose graphs, or you can have a dose rate, such as these. So where can they be applied? So personally, at the NNL, we see it being applied in the areas of design, safety, and decommissioning. Let me explain to you why. So currently, we've got a lot of two-dimensional CAD models. Now, they can get very complicated, as I mentioned earlier. Now, as part of the building information modeling ethos, we are currently creating 3D virtual twins, or using those 2D CAD models, creating live models which can be updated in real time with a lot of little effort. This project has the potential to take that a step further, add in an extra level of detail in terms of dose or shielding data, and that data is more accurate than the ones currently used, which can be fed back into the process, providing confidence to our end user that the end solution is safe and meets all their criteria. These are all the stages involved in the safety case for the laser snake project Lorraine mentioned earlier. There's a lot of them there, and most of these could do with a lot more accurate data, which this project has the potential to provide. It can provide it a lot quicker, a lot less time, a lot less cost, a lot more accurate, and a lot more efficient. And then finally, decommissioning. As I mentioned, NNL are embracing the BIM ethos. So with those 3D virtual twins, we can import them into our software, into our programs, perform next generation simulations, and those the data from those simulations can be fed back into our process to our brainiacs. So, quickly summarize, this is our current design process. It works, there's nothing wrong with it, but it's not very efficient. So with this program of work, this will then turn into, still have our brainiacs at the top, discussing the problem. Instead of making our 2D CAD models, instead of using our clever calcs, we can create the 3D models, import them into our advanced software, and the data from that is a lot more accurate and can be given back to the customer with a lot more confidence. And in the end, we have a very happy operator, but more importantly, a fully trained operator working on the experiment. And finally, it is the 4th of May, as you all know. What you might not know, today is International Star Wars Day. So keeping that in mind, I'd just like to thank Chris Rhodes, Brendan Perry, Zara Hodgson from the NNL for their help in making this project a success, Rob Scott, Craig Hamer from the NAMRC, and Michael Luca and Iswan Stoke from the Institute for Energy Technology. Thank you very much.